All right, so this is coding for Sandy Bridge. And what we're going to do actually at first is go over a little bit of the architecture of Sandy Bridge and go through and show what is different about it and why a closer study of the architecture actually reveals some interesting progressions in the way that Intel is moving their technology. If you look closely at this, you can see where the ultrabook style technologies are going in the future. So let me show you first of all a promo video that highlights some of the multimedia capabilities which are built directly into Sandy Bridge. Where did my promo video go? Of course, it's in Internet Explorer, which is crashing. Here we go. So. These are built-in technologies that are in the silicon of Sandy Bridge. And there's no sound.
Visuals, a suite of technologies integrated into the processor that delivers stunning visual experiences. Let's take a closer look at these graphics and visual technologies. Intel QuickSync Video uses dedicated hardware to accelerate video encoding, enabling blazingly fast synchronization of videos across devices or when sharing videos on the internet. Intel Wireless Display 2.0 lets you stream up to 1080p premium content wirelessly onto your big screen to maximize the entertainment value of your personal and online content. Intel Insider lets you unlock a whole world of premium HD movies and entertainment when they're available on Blu-ray with your second-generation Intel Core processor-based PC. Intel InTrue 3D technology enables you to play the latest Blu-ray stereo 3D movies right from your PC.
That's the video, apparently.
Just use HDMI to hook your PC to your 3D-enabled TV and put on your active shutter 3D glasses. Intel HD graphics is now built into the processor. This high-performance feature means lower latencies and enables superior mainstream gaming and enhanced 3D experiences without the need to add a discrete graphics card. Intel Clear Video HD technology delivers picture-perfect images using a variety of advanced visual technologies that optimize high-definition video playback and provide sharp image quality. Intel Advanced Vector Extensions, or Intel ABX, extends the Intel 256-bit instruction set to speed 3D and other vector operations. These built-in visual features combine to significantly improve your overall graphics and visual experience.
Okay. So for those of you who don't know, Sandy Bridge is the higher-end desktop processors that Intel creates. They are going to be in the ultrabook class of computers, and these are a parallel line to the Atom processors, which are in more of the netbooks and nettop. But looking at both of them, both the architecture of the Atom and Sandy Bridge, you can see parallels. For instance, the integration of the graphics directly into the chip, integration of the memory controllers and the I/O controllers directly into the silicon on the chip. And so by looking at the evolution of both of these, we can see some of the major themes that Intel has in their chip design. So this is a fairly well-known graphic, but it's worth saying again, Intel uses a tick-tock method of microprocessor release management. Starting all the way back with Core 2 Duo, every 6 months, Intel will either redo the microarchitecture of the CPU, and then on the other 6 month, the talk month, they shrink the manufacturing process. So for instance, back with the Halem, for instance, there was a 45 nanometer high gate technology lithography being used to actually create the CPU. But on the top side over here, Halem was a new architecture, and then Westmere, that new architecture shrank down. So with Sandy Bridge, there's a brand new microarchitecture in the processor, and it is probably the most radical change in Intel architecture since the cross-star Pentium. It's a very large change both in the graphics processing, in the way in which different parts of the CPU talk to each other, as well as within caching on the CPU. So here's the last couple of CPUs, going back to Nehalem, and the technologies that were introduced. And these are all technologies that you as developers can code to. You can use Intel's SSE4 instruction sets, which are used for parallelizing floating point operations and graphics operations. Cryptographic functions are starting to be built directly into the processor to speed up AES, and Rheindal, and random number generators. Actually, random number generators coming more in later architectures. Fast memory latency, the caches are being sped up. They're put on the same ring that's being shared with the graphics processor and the I/O controller. So caches are being integrated more into the overall chip. And fast unaligned memory support means that when you're reading sections of data from memory, your data doesn't necessarily have to be aligned to the memory alignment in order to be able to use Intel's instructions to pull that data out quickly. It's a very low-level operation, but it makes a big difference. And later on in the talk, I'll show you some compiler options that you can use for turning those on and off.
What is half float support?
That's a good question. I think it has to do. Does anybody actually know? I'm not entirely sure what that is.
Okay. I never heard of it either.
So this is an overview of the Sandy Bridge processor. And I'm going to talk to several of these. Actually, the Turbo Boost technology is on the next slide, so I'll kind of skip over it for now. But Sandy Bridge has either a 2-core or a 4-core architecture with the graphics unit and the system agent integrated directly onto the die. This is the first time that the system agent, which includes the memory controllers and the media engines, have been directly in silicon and not in on the CPU die, as opposed to in a different chipset. So there's a high level of quick communication in between those portions of the CPU. The next generation media graphics processor, like I just said, is up in the system agent area of the CPU. This is the part of the processor which is involved in media decode and encoding. Sandy Bridge is the first CPU that has an encode engine as well as a decode engine, which supports H.624, VC1, which is like your Blu-ray and HD graphics, video formats, and ABC, which is another industry media format. Discrete graphics support built directly into the CPU. The Sandy Bridge architecture is an architecture that connecting these components together is done in such a way that they can add in more cores in later versions of the CPU. And the architecture that's in place will accommodate that. Before, the way in which different system components talk to each other was through a direct communications medium. Now there is a ring architecture which allows the graphics, the cores, and the system agents to all share the L3 cache. But they're all different stops on the same ring architecture. So if you've worked with network topologies, for instance, a ring architecture is a network topology which is not very robust if there's high failure rates, but it's a robust, if the nodes are there and there's no high failure rates, it's a robust way for sending messages around. And the algorithms that are used for routing are fairly complex. They always take the shortest path instead of going around the die. Integrated memory controller, that's part of the system agent again. And hyper-threading technology, which is now built into almost all of Intel's CPUs. Hyper-threading technology, if you don't know, lets you run one thread on the CPU at once. So this is the look at Intel's Turbo Boost technology. Turbo Boost is a technology that lets you take advantage of the fact, or the lag rather, in between ramping up the frequency of the CPU versus how much time it takes. When you ramp the frequency of the CPU up, the thermal conditions are going to respond by rising. The heat level is going to come up. But there's a lag difference in between how quickly you can boost the frequency and how quickly the thermal envelope raises to its maximum value. And so Turbo Boost gives you a fast bit of performance that will heat up the processor, but then the frequency is ramped down as the heat, the thermal limit reaches its maximum point, the sustaining power point. So this bottom red dotted line is the heat rising, whereas the green dotted line is the frequency of the CPU. Are there questions about that? No? Sandy Bridge has a fast instruction cache. Intel processors, in general, when you write assembly code, those are what Intel calls macro operations or macro ops. And internally, those are converted to micro ops within the CPU. Micro ops are more akin to the older RISC style of CPU instruction. So several macro ops might be decoded into, or one macro op might be decoded into several micro ops. But for the majority of the macro ops, I think it's around 96%. You can convert them in one-to-one with the micro ops. Sandy Bridge includes a micro op cache. So it's the first processor that allows you to store those micro operations rather than decoding the macro op again. And when it does store them, the processor actually turns off the portion of the CPU which decodes operations, so it's a power savings. So you get a caching and a power savings. That's all done on the same level as the L1 cache. The branch prediction unit is entirely redone in Sandy Bridge. This next slide here. The branch predictor is a part of the CPU which looks at branching statements, so ifs or whiles or different types of conditional statements in the CPU. And the instructions will actually, what they'll do is they'll run multiple parallel paths of the code, guessing which one will be the most effective to run. If it happens to guess correctly, those executed statements will be run, but if it doesn't, it has to go through and run the normal path. So there's a speed up if it guesses correctly, and a performance hit if it doesn't. So Sandy Bridge, rather than maximizing the amount of guessing that it can do, which is very power intensive, what they've done is they've tried to optimize the way in which the algorithm does the guessing so that there are fewer faults. So rather than loading a larger history, they try and minimize the faults. And the fault levels in Sandy Bridge are usually down to around 7%. So 7% of the branch predictors will fail. So if you can move that 7% down to 6%, you've got a very large percentage gain in your CPU's ability to branch predict. The memory cluster is enlarged to 256-bit to support the ABX instructions. We'll talk more about those later. And the out-of-order execution buffers are, there are more of them, more execution units in Sandy Bridge than in previous processors. So here's the ring interconnect. The ring interconnect is a part of the system that connects together the graphics, the CPUs, the system agent, and memory controllers. And it runs at the core frequency of the CPU. So it's a testament to how well integrated into the CPU the graphics are, that the graphics are just another step, another stop along the system right here. So they're at the core frequency and core voltage, and they go through the minimum. The routes that are taken are minimized by various algorithms that Intel has built within the chip. This particular type of architecture is scalable to more cores.
Does the ring architecture allow multiple packets on the ring at the same time, or is it one packet per ring on the instant?
There is a size to the amount of data, and I don't want to quote it wrong, but there is a certain maximum size to the amount of data.
Okay, so it's one packet of a large size.
Yeah. Yeah. So the graphics unit, again, is built directly into the chip. Here's the diagram of that. Sandy Bridge supports up to DirectX 10.1 directly within the CPU. However, the media encoding engine, which actually plays back H.26 video, which plays back your HD TVs, your Blu-ray DVDs, isn't run on the graphics processing unit. That's run on the system agent. So it's separate from the graphics processor, which is new in the Sandy Bridge architecture. And in doing that, they're able to optimize those particular types of operations, and they saw almost 50% power reduction in laying in silicon those particular operations rather than running them through the graphics processor. So separating those out were a big win, power-wise. Quick sync video. I've alluded to this quite a bit already, but built into the silicon, you can encode and decode H.264 MPEG-2 and VC1.
This means less power consumption by playing video on the.
Yeah, it does, because the decode operations themselves are laid into the silicon rather than running at a slightly higher level on a graphics processor, which may be software programmable. These are directly laid into the silicon, and so you can get quite a bit of a power reduction by doing that. Here's a diagram of the media encoding engines. One thing that you can do also with the media encoding engines is similar to some of the functionality that NVIDIA and ATI have supported before in the past, or support now actually too. And that is, you can denoise filter, you can do de-interlacing, you can do different types of video transformations on the fly. And Intel is working with software vendors right now in order to implement those at a production studio level where the software has the ability to access these functions. And I'll go through and show you the libraries that are used to do that in a bit. Here's a picture of the video encode engine. There's not too much more to say here. So there are several technologies that are very heavily marketed within the core processors. We already went over Intel's Video Quick Sync, which is the encoding of video, the H.264 and other formatted videos. But there's quite a few of other technologies which are built directly into the silicon. There's Intru 3D, which is a technology that enhances 1080p playback. So this is as you can imagine, great for DVD video, for gaming. Intel Clear Video HD technology is a color enhancing and fidelity technology that's put into the silicon. The wireless display technology lets you take 1080p video, and if you have a wireless receiver connected to your television, will let you stream it directly to your television or other devices. And HD graphics, again, playback directly within the silicon. The Intel advanced vector extensions are great for gaming and for game development. They actually increase the register size to 256 bytes for floating point operations. So what this means is that with one CPU instruction, you can actually do calculations on 4 32-bit floating point numbers simultaneously. So if you're rendering a scene in which you have multiple objects which are moving in a similar pattern. Maybe a piece of cloth is moving on the screen. There's a demo with cloth, actually, I can show you later. But these things can be rendered in parallel. So in gaming, oftentimes you think of parallel execution being done on different CPUs, you can also do them directly within the floating point registers themselves. So this increases the amount of parallelism you can put into your games. ABX targets video editing, audio, image processing, 2D and 3D rendering. It also does all sorts of other corporate type services, CAD, auto, financial services, anything which requires large amounts of computational scientific power. So we've talked about the shift from 128-bit to 256. I'm going to go through these a little faster and go onto the library so you can see how to actually use these within your games. So here's. Did you have a question?
Yeah, they have float as 16-bit.
Okay. All right. So you as developers, you want to know, these are great. You can look at the architecture. There's a lot of dry technical information that's embedded there. But how do I actually get my game to use these technologies? How do I speed up what I'm doing? And Intel includes a wide range of tools and utilities, software libraries, which will let you as a programmer take advantage of these new operations that are built into Sandy Bridge. So one of the first ones is Composer XE. Composer XE is it's a debugging studio, which will let you deep dive down to the very assembly level, or it'll actually let you look at a particular line of code and it'll say how many wake-ups does this particular line of code cause my CPU to have? What's the power state? What's all the associated information with this particular section of my code? And it's for deep diving into your into debugging the power states. The integrated performance primitives. These, I think actually I have. Let me check on the next slide. No? Okay. So the integrated performance primitives provide all sorts of transformations. If you're working with audio or video, you have sine, cosines, various Fourier transformations, other mathematical transformations that are highly optimized for Intel processors. They're parallelized, and when there's more than one CPU, the software automatically takes advantage of multiple CPUs in order to perform your calculations as quickly as possible. The math kernel library is the same idea. Your mathematical operations sped up. Threading and building blocks is a library that Intel provides that provides thread management classes, that provides classes to do multi-threading on CPUs seamlessly.
Quick question on those.
Yeah.
So let's say you were to create a project using, say, all of them.
Okay.
And you deploy it and somebody's running it on a Pentium D.
Mm-hmm.
A, does it work? And I mean, granted, you're not going to get any speed up, but what's the backward compatibility in that case?
So usually if you're using extensions like ABX, there are certain compiler options that you'll build into your executable. Sure. And so you can enable those to get speed ups on CPUs that support them. And on other CPUs, it'll, I need to be sure of this, but I think it'll just run them. But
yeah, an emulation layer.
Yeah.
Okay.
So the software architecture analyzer is a static source code analyzer, which will go through and show you areas that you can improve. It finds security flaws. It also finds bugs and shows you how you can improve your performance directly on a Sandy Bridge processor. And then, of course, ABX. These toolkits are supported within both Microsoft Visual Studio and GNU GCC version 4.4.4. So that's that might be the latest version. I think it is the latest version of GCC. And GDB also supports it as a version 7.1. You see on the Microsoft compiler, you can just use the ABX compiler flags in order to put ABX instructions in your code. So here's the compiler flags that you use with the Intel compiler. I'll go through these quickly and let you browse them online. There's more documentation online that you can go through to educate yourself about the compiler options. Here's some more detail on the integrated primitive performance operations. So to give you a little more information here, I put down filtering, convolution, correlation. You can find everything they can do on their site. The Intel advanced vector operations, again, they're there for floating point operations. The math libraries include all sorts of information. I just took a little bit here and put it here, but I'd recommend you go to Intel's software development site and look up the manual pages on these. So the takeaway I think from this slide is www.intel.com/ABX, and you can find more information about the ABX processing instructions and how to use them. There are all sorts of online tutorials on how to use them with audio, how to use them with video, how to go through and optimize a game that you've already written in order to use these. So I really highly recommend that you go there and look at the information that's available. Okay, so for the demo, I'm going to disconnect this computer, and I'm going to give you a tour of Intel's graphics performance analyzer. And it's a software which lets you take your game, 3D game, and collect all sorts of statistical information on the performance of a particular area. So you can isolate one particular frame or two particular frames or a section and deep dive into what are the vertex shaders that I'm using, the pixel shaders, what DirectX calls am I making, how is that affecting the GPU, how is that affecting the CPU. Just a moment. Hopefully it should be coming up now. First thing I'm going to do is show you the ABX cloth demo. And this is a video which shows off how ABX can be used to parallelize graphics processing on your computer, your game.
This cloth sample demonstrates ABX, the advanced vector extensions available on Intel's latest Sandbridge microarchitecture. ABX brings 256-bit single instruction, multiple data, or SIMD processing to the CPU. For our sample, we chose to apply SIMD parallelism by simulating 8 disjoint or separate pieces of cloth at a time. This lets us take full advantage of ABX and maximize the flop's performance on the chip. The main hotspot of cloth simulation is updating all the constraints or springs in the cloth mesh. With a reasonable stiffness, this requires a handful of iterations per frame. With the typical distance constraint solver, iteration throughput is about 40 cycles with a hand-optimized code to adjust each pair of inputs to be closer to the rest length. Doing 4 or 8 at a time instead of just 1 does not slow down the loop significantly. Consequently, scaling with increased SIMD register width is nearly linear, resulting in a very noticeable improvement in the overall frame rate of the sample. By exploiting all the ABX floating point processing power, a single x86 core is able to drive a significant amount of cloth content. Admittedly, SIMD with SOA is not an approach normally considered for objects with such a large data footprint. Usually, people think of multi-core when they think of coarse-grained parallelism. Nonetheless, the scaling demonstrated in this sample shows this programming pattern may have untapped potential.
Okay. And Intel's Graphics Performance Analyzer is a suite of tools which lets you take a 3D game and analyze the state of the system as well as all the graphics calls that are done within it. In order to start it, you go to the Intel GPA Monitor. In this case, I believe it's already running, so it'll tell me that. Yeah, okay. It's down here. You can right-click on it and add games that are to be monitored to the list here. So here we have a sample 3D scene. As you can see, I can move around the scene. I can go below or above. I can straighten it out, look directly up the staircase. I can change the textures, the wireframes, and I can configure some animation to occur. Up at the top, in the upper left-hand corner, you'll see what's called the heads-up display. Now this is the overlay that GPA will put onto the actual game itself, so the two are independent. But this overlay up here will tell you what the frame rate is, what version of DirectX you're running, and what the resolution that you're currently mapping is. By hitting Control F1, you can pull up configurable information, and there's a long list of information that can be shown here. So you have the CPU load. These are the ones that I just configured here for this demo. The CPU load, the number of draw calls, the GPU busiest state, and the GPU frequency. So if I hit Control F1 again, you can see all the options that you have. Now, your goal right here is to determine whether you are in a particular bad area or an unoptimized area of your game. You want to find out whether you're CPU bound or you're GPU bound. You want to find out if it's your AI logic that is slowing down. You want to narrow down to a single point where you can analyze and then deep dive into it. So that might include doing things like, if you look down at 2x2 textures, Control Alt and 5, you can get different information. 2x2 textures, what it does is it removes all the textures you're sending to the GPU and replaces it with a texture map, which is easily cacheable within the texture cache. One of the most useful tests to do right out of the box is to use the null hardware test and to combine that with disabling the draw calls. Null hardware, what that does, hardware in this case refers to your GPU. So you can run your game, and then whenever a GPU call is made, the GPU call, instead of sending information to the GPU, the frame analyzer will circumvent that and immediately return the function. And so what that does is it simulates hardware which is more or less infinitely fast as soon as it's accessed, it returns. Now you're not going to see any data rendering because of this, but what it will do is it'll let you say, if my GPU is not a bottleneck, if it's infinitely fast, what is my program going to behave like? So we'll do that now. And you can see I went from around 60 frames a second to 350 frames a second. So in this particular case, we can really quickly say that this demo is GPU bound. And if we want to zero in on a particular frame or a particular area, we can deep dive into the GPU calls that are being made. So Frame Analyzer also has a companion software suite called Platform Analyzer. And Platform Analyzer will take a look at your CPU, your memory, what your system is doing, not your GPU. The two are complementary programs. In order to use Frame Analyzer, you do what's called a trace capture. So Control-Alt-T. What wasn't it? Control-Shift-T. You can see up at the top it says that it captured a particular set of frames there. Is it really time?
No, you're good. Sorry, I'm just tired of sitting.
Okay. So I just took that trace capture file, and I will pull up Frame Analyzer. I think these are older samples that I took. This is Frame Analyzer. This is for getting every bit of information that you can get off of your Intel graphics hardware. It also works with NVIDIA and ATI graphics hardware, but you're not going to get the same level of information down in the vendor-specific areas. But things like GPU duration and GPU frequency, those sorts of things we can get from any sort of graphics processor. The top portion here is called the ERG visualization chart. And unfortunately, I don't know why, but when I put it on the overhead projector, a series of options disappear up here. But they give you about 30 sets of data that you can plot along this graph. So if you want to see the pixel shader duration versus vertex shading duration, or pixel, or any of these statistics actually you see right here. If you want to plot them against each other, you can do that really easily here. The blue lines represent ERGs, which are basically pixels that are being rendered to the screen. So nothing in this particular sample was particularly bad. We can pick out some of the taller ones. In this case, we're plotting GPU duration versus ERGs. So the taller ones represent things which took longer to render within the GPU. You can see down at the bottom, this particular frame, this is the particular frame that I just selected up here. And the ERG corresponds to the violet area. So it's rendering the roof more or less here. Over in the scene view, you can see exactly how many milliseconds it took for the GPU to render that, how much of that was spent within the vertex shader, how much was spent within the pixel shader. You can look at large amounts of information here. And again, I don't know why it doesn't seem to render properly here, but my scroll bar is off the side of the screen. So you can go down for quite a ways and look at all sorts of information. You can see the textures that are being utilized, if I can bring those over, in this particular call. The state gives you information about DirectX calls and all the different APIs that were called here. The Shaders tab shows you the shader code that was used for this particular rendering. And you can actually go down and edit the shading code, your particular shader right here. So if you have an egregious part of your program which renders really poorly, and you've determined that it's the shader which is causing it, you can go and dynamically edit the shader right here within the program and see in real time up here on the ERG plot how that affects your program. So you can monkey around down here, fix the problem, verify that it's fixed by whatever metrics you deem necessary, and then take that and incorporate it back into your program. So you can really deep dive. Experiments can show you what would happen if you use textures that are cacheable, or a simple pixel shader, or a 1x1 scissor-rect. And there we go. So that is the frame analyzer. Are there any questions about that? Okay. For more information about this, I guess the takeaway from this is that Sandy Bridge is an entirely new architecture where it closely fits the definition of a system on a chip. The graphics are integrated, the media playback is integrated, the I/O controllers are integrated, video and audio encoding are both integrated. And it's on a chip which has an architecture that's expandable to the future. So you'll see the next series of processors coming out and building upon this architecture that was laid down here. The Intel libraries are the way that you as developers can access these architectural improvements and put them directly into your game. And we also provide tools that let you go through and analyze your graphics and see, if you change various portions of it, how does that affect my game? So you can really figure out, if I use ABX, how does that help my game or some other technology? Any other questions? Okay.